So, hello student. Today we will discuss one of the central theorem of Markov process, discrete time Markov process. This is called Markov Convergence theorem. Okay. So today's topic steady state behavior and Markov convergence theorem. This is also called steady state convergence theorem. So you can you can get both the name in literature, steady state convergence theorem. Okay, so this is kind of central topic in the whole discrete Markov chain theory. Okay, so now let me start with a simple question. Okay, so questions. So you can ask many questions, whatever we learned so far. So for example, we learned these transition probabilities R, I, J, N. Transition probabilities, these are called n-step transition probabilities, right? So the natural question is that does this transition probabilities has a limit? So thus this has a limit. So this something whatever. So we define these limits by a symbol, say pi j. Okay, so does this n-step transition probability is a limit. Okay. Or you can ask like so does this limit does this pi j's depend on the initial state or not? So the way I define the limit, you can understand that this does not define on the initial state, that we will see after some times. Okay, so these are a natural question to ask. Okay, and then we will see that it may or may not be the case. Okay, and okay, so let me give an example, then you will understand. Now you recall that this transition probability graph. So we define one transition probability graph like with a few states, like so a equal to 1 and then 2 is there, and then there is a so this directed graph means the state going from 2 to 1 is with positive probability, right? So it means that p 2 1 greater than 0 is positive probability, and then you have 3 and then 4. Okay, so these okay, and then this. So and then it may have this or something like that. And then we already showed that this becomes one recurrent class and this becomes another recurrent class, right? And this is some say R1, R2, and this is your T constant of only single elements. Okay, the transient state. So so question is that for example, what is the probability that state in the long term the state will be stationary at say 0.1. So for example, you start with 3 and then you go to 4 and 3 and 4 and 3, you cannot come to 1, right? So in my first question what I asked, uh, this has a limit or not, it is always not true, right? So this so if you start with this, so what is the case? The case here, the state Markov chain state, you see T union R1 R2, right? And now you see that when you have if there are more than one recurrent class, then uh, this R I J N may or may not exist, right? May or may not exist, right? Because if you start with 3, then you cannot come to 1. But if you start with 2, you can come to 1 or 3. And if you come to 1, then it will be there, right? So in the long term, if you start with 1, then long term it will be always 1. If you start with 2, you can come to 1 and it will be always 1, right? So what does that mean? In that case, it exists, but sometimes it may not exist. So it depends on the initial state. Okay. So this is one such example where you may or may not have this limit, but there may be another example. So this is one example. Now example number 2. Suppose that so now I am assuming that there is only one recurrent class. So assuming that there is only one recurrent class. This is my assumption. Okay, so then the case is that what happened to this case? Like, for example, you have say recurrent class 1 and then 2, okay, and then let's say 3, and then this, okay. Now here you see that if you start with 1, then you can come to either 1 or 2, and then if you come to 2, then you will go to 3, and then 2 and 3 and 2. So what does that mean? That means if you start with 2, every odd many times you will always land up 3, and even night time you landed up 2. So what does that mean? That means if you start with you want to know what is this P say n2. So Pn2 means that n is the time, and you want to know that whether uh, it will be stationary or it will be limit will be always 2. It will come to always 2 for some. Okay, so this is maybe I can write down I2. So I am I. Okay, so it doesn't matter from where I am starting. Okay, so let me write down the proper symbol. So so P22 n. So you start from 2 and you want to know that after n many times whether it has a limit or not. So that this does not has a limit, okay, does not converge, okay, to any state, okay. Why? Because you see when n so it started 2, right? Initial state is 2. So when n is of the form 2k even, then this then so then it is at 2, but when n is say 2k plus 1 odd, then it is at 3, right? So it's oscillating. So in this case this is oscillating and this limit does not exist, right? So now the case is that so if I remove both these condition, if I choose the condition that which is neither having more than one recurrent classes, so that means only one recurrent class, and also it is not of this form. So this is what, so this kind of recurrent class is called period, right? It is learned already. Okay, if it is a period, then also you don't have a limit. So if I remove both the condition, period and more than one multiple class, does there is a limit or not? Okay, and this theorem, this is a very famous theorem, and this is called Markov convergence theorem. Okay, Markov convergence theorem, or steady state convergence theorem. What does this theorem tell? This theorem tells that if you remove those two conditions, so for example, so let M be a Markov chain, MC mean Markov chain, okay, with a single uh, recurrent class. Okay, suppose I am assuming that single recurrent class and aperiodic, it's not periodic. Okay, if these two are the case, then what happened? Then the states J are associated with the steady state probabilities phi j, steady state probabilities phi j, okay, and having following, satisfying the following properties, that is find the following properties. So what are the properties? So the first property number 1, that limit n tends to infinity or ij of n has a limit, and this is my pi j. Okay, so what does that mean? That means um, uh, it has this probability will be stationary, and with that probability the state will be state j will be achieved. Okay, and it doesn't matter from where you are starting. So this initial, so this pi j does not depend on I, right? That is initial states. So it doesn't matter from where you are starting, it is always having a stationary state. Okay, and then property number 2, that this pi j satisfy this condition. So pi j satisfy this equation. So pi j's are summation k equal to 1 to m. So I'm assuming that my m is nothing but cardinality of S. So there are finally many states, a number of states, and this is pi k and pkj. Okay, this is true for all j equal to 1 to m. Okay, and obviously you see that when you take sum, for example, sum over pi k's, k equal to 1 to m. Okay, so this sum has to be 1. Okay, so I will come to the proof of this statement. So maybe we can give the proof right now. So how to prove this kind of statement? So you know that this in-step transition probabilities. So you can write down these as in terms of, this is only proof Chapman-Kolmogorov. Okay, so R I so R I K and then n minus 1 and then P K J, right? K equal to 1 to M. So this is Chapman Kolmogorov equation, right? Now if we have, so in the first condition we assume that this limit this probability has a limit on n tends to infinity, and this is also the same limit then, right? So this limit n tends to infinity r I j n, it is pi j, and limit n tends to infinity r whatever I k n minus 1 equal to, this is phi k, right? Because n tends to infinity means n minus 1 also tends to infinity. Now using this limiting value, you can easily find out that the equation becomes like that: ij equal to summation pi k into p kj, right? This is very important equation, and this equation are called actually, so there are m many equations, right? And they are called something called balance equation. They are called um, balance equation. Okay, so this proof is simple, that it gives you the balance equation. And now one more property, property number 3. So again one more thing one can ask, so why this summation of this condition is true? Okay, so this kind of tells you that total probability sum over all those probabilities that it will be either on state 1 or state 2 or state m will be 1, right? It can be on any state, so that's why it will probability 1. And now probability 3, property number 3. So what happened to transient state? So you see that if you start with the transient state, say 1 and then 2 and 3, okay, something like that. So you see that 1 is a transient state. So if you start from 1 and then after long term, you can obviously initially you can stay at 1, but after some time you will go to 2 and then you never come back to 1. So what does that mean? In the long term, these transient probabilities are 0 for all transient states. G, okay. And for recurrent state, so these are 2 and 3 recurrent state, okay. For recurrent state you have a positive probability, clear? So okay, so here I am assuming this is periodic, so I have to choose this, okay. So so this is the formula. So this 3 equation gives you this this 3 equation gives you this the beautiful results called steady state probability theorem or convergence theorem, okay. Now let us try to understand this is in more details. So or maybe in, okay, so one question one can ask, so from this equation, from balance equation, one can ask that, so this balance equation pi j equal to summation pi k p k j, Now you can write down this balance equation as like this. So let A equal to Pij. So this will be the transition probability matrix. So A probability matrix. Then this equation is nothing but that means that pi times A equal to pi, where pi is the row vectors, pi 1, pi 2, and then pi m, right? Clear? Okay, so or you can write down in the complementary sense also, or you can write down that A transpose into pi transpose equal to pi transpose, where pi transpose is these column vectors, pi 1, pi 2, whatever you feel, doesn't matter. Okay, you can write down by this or this. Okay, now you see that A matrix, so the element of A are non-negative, right? So elements of the entries of A are non-negative. T. Hence, you must have learned in linear algebra something called Perron's formula. Hence, by Perron's theorem, the solution exists and unique. Theorems. This system of equation, maybe let me write down the name, j equal to 1 to name, right? Star. Thus system of linear equation given by star has okay, so obviously that depends. So you can say unique solution. So unique will be depends on okay, so solution provided a determinant of A equal not equal to 0. So in this case, if the determinant is 0, then you have unique solution. Otherwise, you can also have this. Okay. So here one will be the eigenvalues for A. You can understand that one is the largest eigenvalue of A. Okay, and then the eigenvector associated with 1. So, and pi, which is say pi 1, pi 2, pi m, be the eigenvector associated with okay, kind of generator of the eigenspace of corresponding to 1, right? So so what does that mean? That means you can say that your pi, this pi 1, pi 2, pi n, uh, they are actually generating some kind of called distribution, right? Because so on transient space it is 0, and non-transient recurrent space it is positive, and total sum is 1. So so you can note that as summation pi k equal to 1, k equal to 1 to m, this pi case, they form a probability distribution, probability distribution on the state space S. Okay, and this distribution is called distribution is called the stationary distribution. Stationary distribution. So why does this name stationary? Stationary means that if you start with this state pi j, okay, and then you will be remaining on the same thing. For example, so if suppose this probability of it's not, so you start at j, which is say pi j. Suppose if this was pi j for j equal to 1 to m, okay, and then you want to know that what is the probability of next transition. So probability x 1 equal to j, okay, and then using Chapman-Kolmogorov, you can find out that this is probability of x naught equal to k into probability pk, right? So this is you are going from one step to two-step probability, okay, and then this is for k equal to 1 to m, okay. So and then obviously this probability alumni pi j, so this pi k, for so this is true for every j. So for k equal to this become pi k, so it's sum over k equal to 1 to m pi k pkj, and pi k pkj is nothing but pi j. So this probability also become pi j. So once stationary means once you start with this j with probability pi j, then all the future probability of future state will be pi j. That's why it's called stationary. Okay. So now these balance equation are going to help us for proving many theorems. So maybe I will describe a few examples, then you will understand. Okay. So now with this example say 1, so it's an absent minded professor has 2 umbrellas that he uses when commuting from home to office and back, office to home. Okay. Now he is absent-minded, so if there is no rain, then he forget to carry the umbrella. So if it rains and an umbrella is available wherever he is, either home or office is available, okay, in his location, and then he takes it. Okay, so you understand. So he has 2 umbrellas and he goes to office and home, come back, and he can carry an umbrella if there is a rain and if the umbrella is with the place. Okay, if not, then he will be keeping he will forget the umbrella either at home or office. Okay, and if it is not raining, he always forgot or forgets to take an umbrella. Clear? Now suppose that it rains with probability P each time he commutes. Okay, each time when he is going to office from home or going to home from office, it has a probability P of raining. Okay, independently. So independently, whether it happened last time or not, independently of other times. Okay, this is given. Then what is the steady state probability? What is the steady state probability? Steady state probability that he gets wet on a given day. So it's long term, you understand? Long term probability. Okay. Now you can you can solve this kind of problem using Markov chain model. Okay. And see here are, so what are the states here? So you have to understand what are the states. So so there are three states here, right? So state, three states. State can be 0, 1 or 2. 0 means there are 0 umbrella at his place, whatever, it can be office or home. So you can write down state I. The state is what? So number of number of umbrella are available. In the current location, wherever he is there. Okay, current location. Clear? So now first we first try to understand what is the transition probability graph. Transition probability graph. How it look like? So it can be 0 umbrella, or it can be 1 umbrella, or it can be 2 umbrella. Three states. Okay. Clear? Now suppose he is a current state, and he there is no umbrella there, current state, and then he will go to the other the probability of he is going to wait, he is going to other place is always 1, right? This is 1. And if there is a umbrella and there is raining, then probability that the current states have, I mean when he is going from there to another place, so the new place is the current place, there will be 1 umbrella, right? This current state will become 2, become 1. So this is probability P if there is a raining. Okay. and if suppose he is there where there is a one umbrella and it is raining with probability P, then he is going to there in the new state where it is having two umbrellas, because already there, see, he has one umbrella, so other umbrella must be in his other place, but when he go to that place it becomes two umbrellas, right? Now when there is one umbrella and if there is no rain, then the umbrella will be there already, so there will be one umbrella and this will be 1 minus P, the complement probability. Similarly, if there is a two umbrella and there is not raining, then he will go to other place where there is no umbrella and this probability will be 1 minus P. Okay, this is okay to everyone. So this is 1, this is 1. Clear? So this is transition probability graph. So state from 0 0 there is nothing, but 0 to 2 can have probability 1 and 2 to 1, right? These are the transition probabilities. Now we can find out the matrix, transition probability matrix, transition probability matrix, that A. So if it is 0, from 0 to 0 there is no probability, right? So it is 0. But 0 to 1 also, 0 to 1 also, see there is no arc from 0 to 1, so that is also 0. Okay, but 0 to 2, uh, from 0 to 2 the probability is 1, so this is 1. Clear? Similarly, uh, 1 to 0 is 1 to 1, 1 minus p, and 1 to 2 p, and similarly 2 to 0, 2 to 0 1 minus p, 2 to 1 p, 2 to 1 p, and 2 to 2 is 0. Okay, so this is a transition probability matrix. Okay, and obviously I am assuming that p is probability being real is in between 0 and 1. So this is the assumption also. So now we can use this Markov convergence theorem or statistical convergence theorem, provided that we need to check whether this system has satisfied the condition. So what are the condition? I recall the condition. It should be first condition was what? First condition was there should be one recurrent class. Now we check how many recurrent classes are there. So you see, first of all, there is no transient state here, right? Because if it is 0, you go to 1, go to 2, then you can come back to 3, and then 2 to 1, 1 to 2, right? So, and then recurrent, so there is only one recurrent class. So this is clear from here that only one recurrent class, right? So condition 1 satisfied already. Now what about the condition 2? Condition 2 that this must be aperiodic. Okay, this cannot be periodic. Now you need to prove this thing. Okay, the proof is simple. This is homework. Prove that. So this is homework. Prove that uh, this Markov chain is aperiodic. Okay, so it is not a period. Okay, so that means satisfy both the condition of the steady state probability convergence theorem, and then you can apply. You can use a balance equation. So what are the balance equations? So the balance equations are this phi 0 will be equal to 1 minus p times I2. Okay. Similarly, phi 1 equal to summation, right? So 1 minus p times phi 1. So this phi 1 is 1 minus p times pi 1 and plus p times pi 2. Okay, and similarly pi 2 equal to 1 minus, so from here from pi 2 it equals to p, so p times not 1 minus p, so coming with p, right? Yes, so p times pi 1 plus 1 times pi 0 plus pi 0. Okay, now we need to solve this equation. So now okay, so for okay, so now look at this equation. So this is C 1 minus p pi 1 and pi 1, so that become p pi 1. So from here you have pi 1 okay, p pi 1 equal to p pi 2 and p not equal to 0, so this implies pi 1 and pi 2 equal to 2. Pi 1 pi 2 both are same, right? Now if we replace those things, then what happened to pi 0? So pi 0 will be equal to pi 0 1 minus p pi 2, right? And pi 1 equal to pi 2. And also we know that we have this equation pi 0 plus pi 1 plus pi 2 equal to 1, right? Now if we replace these two things, then you have pi 2 times 1 minus p plus 2 that equal to 1. So what does that mean? That means 3 minus p. So this implies pi 2 equal to 1 by 3 minus p. Okay, so this is again equal to pi 1. Now what is pi 0 then? Say pi 0 equal to 1 minus p by 3 minus p, right, from this equation. Okay, so what does that mean? That means pi 0 is the steady state probability that in the long run there will be no umbrella with this probability, and then so hence this is the probability, this is the answer, right? This is the probability that he will get with the long run, the steady state probability. Clear? So this is one example. Maybe I can give here are plenty of example. Maybe I will discuss with one more example, and then I will stop today's lecture. Now let's do the second problem. So example number 2, and this is saying that, so suppose a professor works in a circular building with m doors. Okay, m doors, so odd number of doors, and he never uses the same door twice in a row. Okay, so when he use one door to go out or in, then he will use the next another door for that. Okay, so instead what he does, so instead he uses with probability P or p minus 1. So with probability p, use the clockwise directions. Use, and with probability p minus 1, anti-clockwise direction. So with probability the door that is adjacent in the clockwise directions, and with probability 1 minus p, anti-clockwise direction and or the counterclockwise, anti-clockwise direction. Okay. Now what is the probability directions? So what is the probability that a given door will be used on some particular day far into the future. So long term, we want to understand what is happening. Okay. Now how to solve this kind of problem? So you can first draw the transition probability matrix graphs. So suppose node number 1, node number 2, node number 3, and so such and m minus m is odd. So you can go to this with probability p. You can come from there to there with probability 1 minus p, and similarly here p 1 minus p, and so on. Okay, this is p 1 minus p. Okay, and so on. Okay, so now so you can understand that. So m door I choose these are the states 1, 2, 3, m. Okay, and then you can easily find out the transition probability matrix. So the matrix will be what? This is nice form. So its diagonals are always 0. So start with 0, 0, and then 0 to 1, and this is like 1. So 1 to 2 it is going to equal to p, but 1 to 3 cannot go. So these are all are 0 unless the last one. What is last one? Last one is, you see, 1 to m, right? So 1 to m, it is coming from 1 to m with probability 1 minus p. Okay, so last one is 1 minus p, and so this is obviously, you can understand this is m cross n matrix, m cross n matrix. Similarly, for 2, this is 1 minus p, and then 0, and then p, and 0, all are 0, right? So diagonals are all 0, and then super diagonals are p, and sub diagonals are 1 minus p, 0, 1 minus p, 1 minus p. So this is the matrix. Clear? And in the last one is what? Last one is p, and then 0, 0, 0. This is 1 minus p. Clear? Now obviously you can ask questions. That is, I'm giving you homework that satisfy two conditions. One is single recurrent class. This is obvious. You can just check it, and then obviously that aperiodic. You need to check both those things. Okay, so check this thing, and then you can use this steady state probability convergence matrix, and then you can easily find out the balance equations will be of this form: pi 1 equal to 1 minus p into pi 2 plus p times pi m, right, for 1. But for 2 to m minus 1, what happened? When I equal to m minus 1, it will be either I plus 1 or I minus 1. So p times pi I minus 1 plus 1 minus p times pi I plus 1. And this is true for I equal to 2, 3, 2 minus 1. Okay. But for last one, pi m, what happened? It can go to either m minus 1 or 1, pi 1, right? So pi 1 with probability this and probability pi minus 1. Okay. So and now you need to solve these equations. Now if you solve this equation, then you will see from the any two of this equation you can solve. So what do you need to find out? You need to find out that matrix pi, the row vector pi such that pi times a equal to a. And how do you solve these things? So these are called okay, sorry. Okay. Yeah. So and what is this? So this means that you can write down that pi minus pi a, this is 0, and then you can talk about pi times I minus a equal to 0. So uh, so pi is the eigenvectors corresponding to this I matrix A. So how to solve this kind of problem? So to solve this kind of problem, we need to find out the eigenvalues. Directly you can find out by using characteristic equation or whatever determinant, and then you confirm. So this will be the equations, and then you do whatever method you can do, Cramer's rule, blah blah blah, whatever you feel. Okay. So solve these equations. Now after solving this equation, you will see that the answer will be what? That this pi j will be whatever for j. It will be always 1 by n. J equal to 1, 2, 3. Okay. This pi is always 1 by n. So in particular, there is equal probability of using any door in the long run future. So initially he may use some door particular, but if we follow this method of using the other doors with probability p in the clockwise and anti-clockwise with 1 minus p, then in the future long run he will use all the doors with equal probability, right? So see, there are nice problems which attach with the steady state probability and Markov convergence theorem, and there are many more such problems are there. Okay, and then maybe I will stop here, and we will continue many more other interesting problems in future. Okay, so I hope you understood today's discussion. Is very important discussion, and you can comment on in the comment section if you have some question. Okay, so I will stop this here.